Hello friends! Today we are going to examine the physics of macroscopic systems. It is the physics used to describe systems with number of particles on the order of 10 to the power of 23, the Avogadro constant. With such numerous degrees of freedom, keeping track of the motion of each individual particle becomes untenable. One is therefore forced to combine the use of the laws of mechanics with statistics to describe the averages and aggregates of physical observables. And so, statistical mechanics was born. At the heart of this subject lies the partition function, which carries all information concerning a macroscopic system in thermal equilibrium. This is today's topic. Here's an overview of what we will talk about. First, we will look at the concepts of the macrostates and the microstates of a system. It turns out that a single macrostate can be realized by a great number of microstates. Based on these ideas, the Boltzmann distribution, which gives the probability of a system being in a particular microstate, will be derived. From this, we'll get a mathematical definition of entropy and temperature, which conform to our physical intuition. The partition function then arises as a key component to this distribution. To demonstrate the utility of the partition function, we go through a few applications, calculating statistical averages and fluctuations of physical observables. Most importantly, we will derive the 4 laws of thermodynamics. At the end, all the key ideas discussed will be summarized. Number 1. Macrostates versus microstates. Let us take the simple example of a gas consisting of point particles. Furthermore, we are only interested in the total kinetic energy of the particles. We see that the same amount of energy can be carried by many different combinations of particle velocities. Each combination of velocities represents a microstate of the system, which we denote by psi index with a subscript. The macrostate makes no distinction between the different microstates with the same energy. These microstates are just different realization of the same macrostate. In general, a macrostate is a set of variables that gives overall information about a macroscopic system. The total energy of a system is an example of a macrostate, without details of the microscopic configurations that carry this energy. Here we introduce a standard jargon. A microcanonical ensemble is a statistical ensemble of microstates with the same energy. Its key feature is that all microstates in this ensemble occurs with the same probability, if you measure the total energy of the system. That's because one has no way of knowing which microstate the system is in, based on just knowing its energy. Therefore, they are equally likely to occur. We denote the total number of microstates with energy E as omega of E. We are now ready to derive the Boltzmann distribution. So what is the Boltzmann distribution? When a macroscopic system has reached thermal equilibrium with its environment, the Boltzmann distribution tells us the probability of finding the system in a given microstate. Thermal equilibrium occurs when the probability distributions describing the system becomes time-independent, after sufficient time is allowed for interactions with the environment to take place and reach their final conclusion. This distribution was discovered in the 19th century by Austrian physicist Ludwig Boltzmann, who was trying to establish a microscopic foundation for thermodynamics. At the time, atoms were still a hypothesis, and this was also the first time mathematical statistics was applied to classical mechanics. So the idea was both novel and groundbreaking. The Boltzmann distribution applies to the following scenario. Consider a system in microstate psi I, having an energy EI, and is immersed in an environment with energy much higher than the system. We assume that they form a closed system with a conserved total energy of E. And furthermore, the walls of the system also allows heat to be exchanged with the environment, but not particles. Under such conditions, the probability of finding the system in the given state psi I is proportional to the number of ways it could exist in this microstate. This is proportional to the number of microstates of the environment that is consistent with the system being in psi I. We denote this number as omega of E environment, where E environment is equal to the total energy E minus the system energy EI. According to the definition introduced earlier, omega represents the total number of microstates in the microcanonical ensemble of the environment. Recall that each state in a microcanonical ensemble has the same energy. We denote a microstate of the environment as capital psi I. Let's take a closer look at omega. To express it as a function of system energy EI, we write E environment as the total energy E minus EI. Then take a log, followed by an exponential of omega E minus EI. Recall that the exponential is the inverse of the log, so this just gives the original omega function. The reason we take a log will be clear in a minute. Remember that we need omega to calculate probability. Next, assuming that E and E environment are both very much larger than EI, a reasonable assumption, we Taylor expand log of omega E minus EI with EI as the variable. We claim that the higher derivatives term of this series can be dropped. This is due to the property of the derivatives of the log function. Looking at the plot of log x, we notice that the curve flattens rapidly with large x. This can be verified by taking the derivatives explicitly. Due to the large powers of x in the denominator, higher derivatives vanish quickly with increasing x. This is exactly the situation where the total energy E is very large compared to EI, and so higher derivatives of log omega E with respect to E are similarly suppressed. And we're left with the truncated series where log omega E minus EI is equivalent to a linear function of EI. Substituting this back into the exponential function and absorbing the term independent of EI into the prefactor, we get the probability of the system in psi I. It is important to note that this probability is considered to be a function of EI, while functions of total energy E are regarded as constants, to be consistent with the physical situation. Before moving further, let's introduce some important definitions. First is entropy. Entropy S is defined as Kb times log of omega E, where Kb is the Boltzmann constant, which converts unit of temperature to energy. At this stage, we can take Se as synonymous with omega E, which is the number of microstates consistent with the macrostate E. We will motivate the log in this definition later. Now we can define temperature T as 1 over T equals ds dE. Later we will show that this definition is consistent with our intuition that heat flows from higher temperature to lower temperature. Next, we introduce the standard notation beta, which is equals to 1 over kBT, and is also equal to d log omega dE. We then substitute beta into the expression for the probability of state psi I. And get p psi I is proportional to e to the power of minus beta ei. We then introduce the normalizing factor 1 over z, such that the sum of probabilities over all microstates equals to 1. This implies that z equals to the sum of e to the power of minus beta ei, known as the Boltzmann weight of state I, over all microstates of the system. The important point is that a microstate with higher weight occurs with higher probability. Z is defined as a function of temperature through beta. Z is called the partition function. It contains information about all the microstates available to the system at thermal equilibrium, as well as their relative probabilities. This means that all the statistical information about the system is contained within it. Hence, the partition function is the most important function in statistical mechanics. We summarize the results derived so far. The Boltzmann distribution gives us the probability of finding the system in a particular microstate during thermal equilibrium. The essence of this distribution is concisely expressed in the partition function. From this, we get the mathematical definitions of both entropy and temperature. Before we examine the physical consistency of these definitions, let's introduce another piece of jargon. The canonical ensemble of a system is the set of all possible microstates it could take when in thermal equilibrium with its environment. Energy is exchanged between system and environment, but not particles. Therefore, the Boltzmann distribution gives the probability of a system being in a particular microstate of its canonical ensemble. Now let's look at entropy. This is prescribed by Boltzmann as S of Es equals Kb times log omega Es, which describes the entropy of a configuration of the closed system consisting of both system and environment, with energy Es allocated to the system. Omega Es is the total number of microstates associated with this macrostate. We denote the joint macrostate of system and environment by psi. Therefore, if S of Es is bigger than S of Es prime, the macrostate representing the energy allocation Es E environment would be more probable than the one with Es prime and E environment prime. But how much more probable? Let's try and estimate. Consider a system of around 10 to the power of 23 particles. This is roughly the number of molecules in 18 grams of water. When the system is in the macrostate capital psi prime, assuming that each particle can only be in two states, the number of microstates associated with this macrostate is equal to 2 raised to the power of 10 to the power of 23. Taking log of this, we have log omega prime equals to 10 to the power of 23 times log 2. Suppose instead the system is in state psi, with the number of microstates omega equals to 10 billion times that of the number for psi prime. Then the fractional increase in entropy due to the system being in this new state is just the unimaginably small 10 to the power of minus 20%. This means with only such a small increase in entropy, a state would be 10 billion times more probable. Therefore, unless there are physical constraints preventing it from happening, it is a virtual certainty that a closed macroscopic system will evolve towards a state of increasing entropy. This is the second law of thermodynamics. Let's now try to answer the question we've asked earlier. Why is entropy defined with a logarithm? Consider the situation when two systems are put in thermal contact with each other. The total energy of this combined system is the sum of individual energies plus an additional interaction energy between the two systems. This interaction is necessary if the systems are to converge to an equilibrium state that is different from both initial states. We can regard this energy as relatively weak compared with the individual energies of the systems, because it scales with the surface area joining them, while the individual energy scales with volume. With this assumption, the total entropy of the joint system is just given by S of E1 plus E2, neglecting interaction. Here's where the logarithm comes into play. The total number of microstates of system 1 having energy E1 and system 2 having E2 is just the product of the number of microstates associated with each energy. Therefore, omega of E1 plus E2 is equal to omega E1 times omega E2. Taking log on both sides just tells us the log of the sum is the sum of its parts. This means the total entropy is just the sum of each individual entropy. The log makes entropy an extensive quantity, which means it scales linearly with the size of the system. This expression for entropy is due to Boltzmann and was famously engraved on his tombstone as one of his crowning achievements. Later we will see a generalization of this and get yet another reason for this log form. We now take a closer look at temperature. Temperature is defined as 1 over T equals to the derivative of entropy with respect to energy. We will now show that this implies energy flows from a region of higher temperature to a region of lower temperature. This is the zeroth law of thermodynamics. Consider again two systems in thermal contact, with a conserved total energy E and individual energies E1 and E2. The total entropy S is given by entropy S1 of system 1 plus S2 of system 2. E2 can be expressed as E minus E1 by energy conservation. Thus the total entropy S is just a function of E1. The variation of S with respect to change in E1 is given by ds1 dE1 times delta E1 minus ds2 dE2 delta E1. The minus sign is due to E1 and E2 changing in opposite ways such that the total energy is constant. Using our definition of temperature, delta S can be written as 1 over the temperature of system 1, T1, minus 1 over the temperature of system 2, T2, and multiplied by delta E1. By the second law of thermodynamics, delta S has to be greater than 0 as the two systems approach thermal equilibrium. This means that if T2 is greater than T1, the inverse of T1 minus the inverse of T2 is greater than 0, which implies that delta E1 has to be positive, that is, energy flows from the higher T2 to the lower T1. Conversely, if T2 is less than T1, everything is reversed, and energy flows from the now higher T1 to the lower T2. It is also apparent that this energy flow will continue until the total entropy reaches its maximum, when temperatures equalize. This can be seen by setting the derivative of S with respect to E1 equals to 0, which determines the maximum point of entropy. This completes the proof that our definition of temperature is consistent with the zeroth law of thermodynamics. We are now ready to generalize the Boltzmann distribution. Recall that this is a distribution describing the probability for a system to be in one of a set of allowable states under thermal equilibrium. This set of states is called the canonical ensemble. While each state in it can have different energies, they are restricted to have the same number of particles. Here, we will remove this constraint and generalize this to the grand canonical ensemble. In this ensemble, particle exchanges are allowed between the system and its environment. As before, the system has an energy EI, with an additional variable Ni, its particle number. These are the properties of the microstate psi that we're interested in. The same assumptions carry over from the canonical ensemble. In addition, similar conditions now hold for the particle numbers, with the total number of particles being conserved. We now introduce another standard jargon. The grand canonical ensemble is the set of all possible microstates a system could take under thermal equilibrium with its environment. Now both energy and particles are exchanged, as in the scenario we've just described. The Boltzmann distribution then gives the probability of finding the system in a particular microstate, psi, in the grand canonical ensemble. This probability is what we are going to calculate. Recall that previously, when there's no particle exchange, the probability of the system in psi is proportional to omega E minus EI, which is the number of microstates of the environment consistent with psi. With particle exchange, omega now has an additional particle number dependence, n minus ni, which is the particle number of the environment. N is the conserved total particle number. Again, we take the log of omega followed by an exponential, in order to tailor expand log omega with respect to the variables ei and ni. As before, the properties of the log function allows us to truncate this expansion, ignoring higher derivative terms, as both e and n are very large compared to ei and ni. While we recognize the coefficient of ei to be beta, the inverse of temperature, the coefficient of Ni gives us a new variable, mu, which is called the chemical potential. This is defined as beta mu equals minus d log omega dn. The minus sign ensures that particles flow from higher potential to lower potential, in keeping with normal convention. We will show this in a moment. Beta and beta mu can now be substituted into p psi I, which is again normalized by 1 over z. The sum of all probabilities equals to 1 implies that z is equals to the sum of Boltzmann weight of all microstates in the grand canonical ensemble. This is the new partition function of a system with variable particle numbers under thermal equilibrium. Note that z is now regarded as a function of both beta and mu. Let's summarize what we have derived. For a system in thermal equilibrium exchanging both energy and particles with its environment, we have now a new Boltzmann distribution giving us the probability for the system to be in a particular microstate. This information is encoded concisely in a new partition function modified by the chemical potential. We also came up with the definition of temperature and entropy consistent with the zeroth and the second law of thermodynamics respectively. And on top of that, we obtain a chemical potential consistent with particle flow towards thermal equilibrium. We will prove this last statement shortly. A quick remark on how the Boltzmann distribution can be further generalized. While we have taken care of variable particle numbers, these numbers can be further divided into different species of chemical molecules, each with a different chemical potential. This allows us to examine the relative proportions of chemicals during thermal equilibrium, and is an invaluable tool for physical chemists. As promised, we now present a proof that our definition of the chemical potential implies that particles flow from higher potential to lower potential towards thermal equilibrium. We go back to the setup where two systems are placed in thermal contact, exchanging energy and particles, with total energy E and particle number n being conserved. Under these constraints, the total entropy S is just a function of E1 and N1. This implies that the variation of S with respect to its variables is equal to a contribution due to the change in E1 and another due to the change in N1. Rewriting this with the definitions for temperature and chemical potential, we have the first contribution due to delta E1 and the second contribution due to delta N1, which is the new term due to particle exchange between system and environment. By the second law of thermodynamics, this has to be greater than zero as the system moves towards equilibrium. Since we have already considered the relation between temperature difference and energy flow, we can just assume that temperature has already equalized and just look at the effects of chemical potential. This means that the temperature term drops out with beta 2 equals beta 1. This inequality implies that if mu2 is greater than mu1, the change in N1 must be positive, and particles flow from system 2 to system 1. Now we see why the minus sign in the definition of chemical potential, so that particles flow from a higher potential to a lower one. Conversely, if mu1 is greater than mu2, particles now flow from system 1 to system 2. This concludes our proof that particles flow from a higher chemical potential to a lower one until the chemical potentials equalize towards thermal equilibrium. Similar to the temperature case, the statement that chemical potentials equalize towards equilibrium is mathematically expressed as ds dn1 equals to 0, which is the condition for entropy to be at its maximum. Let's look at some applications of the partition function. We will be calculating the energy, pressure, and particle number of a macroscopic system that is under thermal equilibrium. This is done by identifying these macroscopic quantities as averages of the corresponding microscopic quantities over the relevant statistical ensemble. Average fluctuations about these averages can similarly be calculated. For example, if we want to calculate x, a macroscopic variable, this is expressed as an average denoted by xi enclosed by an angle bracket. The average is defined by summing over I p psi I times xi, where the psi i's are microstates of the statistical ensemble. xi is the variable x evaluated on psi I, and the probability p is given by the appropriate Boltzmann distribution. As a first example, we will derive the average particle number from the partition function. N is equals to the sum over I, P psi I n I. Putting in the Boltzmann distribution for P, we can see that Ni can be generated by differentiating the Boltzmann factor with respect to mu, and then dividing out beta, which is brought down from the exponent together with Ni. But the derivative of the Boltzmann factor with respect to mu divided by z is just d log z d mu. We can see that the partition function acts like a generating function for the statistical variables of a macroscopic system. Next, let's try and derive E minus mu n. This quantity is chosen simply for convenience. Knowing it together with n from the previous example, we can easily get the average energy E. As before, this is defined by taking the average of EI minus mu Ni with the Boltzmann distribution P psi I. We can use the same trick again to bring down EI minus mu Ni, but this time taking derivative with respect to beta instead, and then correct for the minus sign. And so, we have E minus mu n equals minus d log z d beta. This is our result. Again, we see that the partition function acts like a generating function. We now calculate the pressure of the system. First note that the energies of microstates are actually dependent on the volume of the system. This is due to the fact that work is needed to change the volume of the system. If the volume is changed very slowly, the system will remain in the same microstate, but the energy of that state will change to soak up this work, hence the volume dependence. Work done on the system in state psi I to change its volume is denoted by dWi, which is equal to dEI dV times dV, where V is volume. For the case of compression, this is equal to minus the negative of dEI dV times dV, where dV is negative. The term in the bracket is defined as pressure, which is positive, and is denoted by Pi. The pressure P is then defined by minus dEI dV averaged over the Boltzmann distribution. Note that only EI depends on volume in the Boltzmann factor. Therefore, the term minus dEI dV can be brought down by differentiating the Boltzmann factor with respect to volume, then dividing out beta. This gives the result P equals 1 over beta times d log z dV. Putting together all our results, we see how the partition function can be used to generate average values just by taking various derivatives of log z as a function of beta, mu, and volume. The situation is a little simpler if we do not care about the number of particles in the system. In this case, mu could be set to 0, and we'll just have the regular form of Boltzmann distribution. The average energy E will then be minus d log z d beta. Higher order averages can also be calculated. For instance, the square of energy fluctuation delta E square can be written as the average over I, the square of the difference between EI and E, by P psi I. The term linear in EI in the bracket on the right of P can be evaluated right away by replacing EI by its average value. Therefore, delta E square is given by the difference between the averages of EI square and E square. This gives a more convenient expression for the square of energy fluctuation. Gathering all the equations needed at the top, Let's evaluate the derivatives of log z with respect to beta. As shown before, the first derivative is just the negative of the average energy. The second derivative just acts on the probability distribution P, which carries the beta dependence. dP d beta consists of two contributions. The first comes from acting on the exponential of the Boltzmann distribution, bringing down the minus EI. The second comes from acting on z, which brings an extra power of z in the denominator and a minus sign, as well as the factor dz d beta. From this second term, 1 over z times dz d beta equals summing over I minus EI times the Boltzmann weight divided by z. This is just the negative of average energy. Substitute this expression for dP d beta back into the second derivative of log z. We then have the second derivative of log z with respect to beta equals to negative the difference between the average of energy square and the square of average energy, which is just negative the square of energy fluctuation. This shows that even higher order fluctuations of system variables can be generated by the higher derivatives of z. The partition function is indeed a powerful tool. Let's develop the idea of entropy further. The original expression due to Boltzmann applies to a macrostate of a closed system. Therefore, all relevant microstates have the same energy and equal probability of occurrence. The number of states is given by omega. This was later generalized by American physicist Willard Gibbs to a form that holds for arbitrary probability distributions. Gibbs entropy is given by minus kb sum of I pi log pi, where pi is the probability of state I. To see that Boltzmann entropy can be derived from this expression, apply to it a uniform probability distribution with all pi's equals to 1 over omega. This gives S equals minus kb sum over I 1 over omega times log 1 over omega. Since the summands are independent of I, the sum over I just gives an extra factor of omega. And we end up with Boltzmann entropy. As mentioned before, Gibbs entropy holds for more general probability distributions, not just for Boltzmann distribution, which only applies to systems under thermal equilibrium. It is valid even when the probabilities are still changing with time and far from equilibrium. Using Gibbs entropy and Boltzmann distribution, we will now prove the three laws of thermodynamics. One thing to notice about the Gibbs entropy is that it is always positive. We claim that it is a measure of uncertainties within a system. To see why, suppose we are 100% sure that the system is in state psi1. This means that P1 is the only probability that is non-zero and is equal to 1, which implies that the Gibbs entropy is equal to 0, due to log 1 being 0. Therefore, there is zero uncertainty about the state of the system. This is consistent with our certainty of the system being in psi1. Whereas if all probabilities are equal, and we are 100% uncertain about the state of the system, the probability of each state is equal to 1 over the total number of states, omega. Applying this to the Gibbs entropy gives S equals kb log omega, which is the maximum value of S. Note that it is a mathematical fact that a uniform probability distribution maximizes the Gibbs entropy. This shows that S measures the uncertainty of the system. The third law of thermodynamics states that at absolute zero, the entropy of the system will reach its minimum value. This can be seen in the following way. At t equals to 0, the probability of the system being in its ground state goes to 1. This is due to the fact that the partition function is dominated by the Boltzmann weight of the ground state. All the other contributions are suppressed exponentially relative to it, as t goes to 0 and beta goes to infinity. This certainty of the system being in the ground state implies that S equals to 0, its minimum value, thus proving the third law. We now prove the second law of thermodynamics, which is the statement that entropy will always increase with time until thermal equilibrium is reached. The Gibbs entropy depends on time through the probability distribution, so its time derivative is equals to minus kb sum over I dpi dt times log pi plus pi times d log pi dt. The second term within the bracket becomes just the time derivative of pi once the derivative of log pi is evaluated. We find that this term is just the derivative of the sum of all probabilities, which must necessarily be 0. This leaves just the first term. The next step would be to evaluate dpi dt. dpi dt is given by the following, where the absolute square of Vij is the transition probability rate from the state psi j to psi I, while the absolute square of Vji is the rate for the reverse process. The first term on the right-hand side increases pi and is the sum over all contributions where the initial states j make transition to state I. Each contribution is the product of the probability to be in state j, pj, multiplied by the transition rate to I, given that the system is in state j. The second term, which reduces pi, sums over all possible ways for the system to transit away from state I. Each contribution consists of the product of pi with the transition rate away from I to some state j. Furthermore, it is assumed that the microscopic processes involved are time reversible, which implies that Vij equals to Vji. This means that dpi dt could be written as the sum over j, the transition rate from j to I, multiplied by the difference between pj and pi. Let's substitute this expression for dpi dt back into the earlier equation for ds dt. We then obtain ds dt equals to minus kb times the double sum over ij, the transition probability from j to I, times pj minus pi, multiplied by log pi. Notice that even if we interchange I and j in the summand, under the double sum, the result of the sum remains the same. Therefore, we could replace the summand with one that is symmetrized between I and j. Now using the fact that Vij equals to Vji, ds dt is equal to minus kb sum over ij half times the transition probability from j to I times the difference between pj and pi and multiplied by the difference between log pi and log pj. Notice the difference between pj and pi and the difference between log pi and log pj are opposite in sign. This means that the product of the two brackets is negative. Therefore, the time derivative of entropy is always positive. This completes the proof of the second law of thermodynamics. And we have achieved this purely by using the definition of Gibbs entropy and the assumption of microscopic time reversal symmetry. But there's a caveat to this last assumption. In elementary particle physics, there are actually processes that violate time reversal symmetry. These are called CP violating processes and are driven by the weak interaction. We will safely ignore such processes as they are too weak to figure in our applications. Now we will prove the first law of thermodynamics. It is a statement about the change of a system's energy under thermal equilibrium, and is often associated with the conservation of energy. Starting again with the Gibbs entropy, we use an identity derived earlier. The change in entropy equals minus kb sum over I dpi times log pi. This is obtained using the fact that the sum of probabilities is always 1 and does not change. Log pi is expanded further using the Boltzmann distribution for pi. Thus, the condition of thermal equilibrium is introduced. The expansion gives minus beta ei plus beta mu ni from the exponential and minus log z from the normalization factor. This last term with no I dependence leads to the sum of dpi's, which gives 0. We are then left with ds equals 1 over t sum over I dpi times ei minus mu sum over I dpi times ni. Here we have used the definition for beta. The first term can be rewritten as two terms, the total differential of the average energy minus sum over I pi dei. The differential of ei in the latter is equal to the partial derivative of ei with respect to v times dv. Recall that ei has a volume dependence. Using the earlier definition for pressure, we could write minus sum of I pi dei dv as pressure P. This means the first term within the bracket is equal to the change in energy plus work done by the system. We are then left with the last contribution to the change in entropy. This is the sum over I dpi times ni, which is the change in average particle number, n. Note that n can only change through the probabilities, since the range of possible values of particle number never changes. Putting everything together, we have ds equals 1 over t times dE plus p dV minus mu dn. Rearranging this gives us the more familiar form in terms of change in energy. This concludes the proof of the first law of thermodynamics. All we have used are the Gibbs entropy and the Boltzmann distribution. We can see three contributions to the change in energy of the system. The first is heat, defined by TdS, and its energy in the form of random motion. The second is just the work done on the system. The third is due to the introduction of particles into the system. Here we can see what the chemical potential mu really means. It is the minimum amount of energy added to the system by adding one particle. Minimum because it excludes thermal agitation, and is just due to the chemical interaction of the particle with neighboring particles. Now let's summarize everything we have learned today. Macrostates are a coarse-grained, aggregate view of a macroscopic system. They can be realized in many ways through microstates, which carry all microscopic details that are not of direct interest. Therefore, all these microstates occur with the same probabilities for a given macrostate. The number of microstates omega in turn determines the probability of a system to be found in a macrostate. This reasoning is the foundation of statistical mechanics. From the concept of microstates follows the idea of entropy, an extensive variable derived from omega. This idea also allows us to derive the probability distribution of microstates of a system under thermal equilibrium. This is the Boltzmann distribution and its concise representation in the partition function. One also gets out of this a definition of temperature consistent with the zeroth law of thermodynamics. Pursuing the development of entropy further leads to Gibbs entropy, which generalized Boltzmann's idea to a measure of uncertainty of an arbitrary probability distribution. This allows us to study even states that are out of equilibrium, and shows how Boltzmann entropy is reached on approaching thermal equilibrium. Further applications of the Boltzmann distribution allow us to calculate ensemble averages such as average energy and its higher fluctuations. Finally, combining the powers of both Gibbs entropy and Boltzmann distribution, we prove the three laws of thermodynamics, with only the added assumption of microscopic reversibility for the second law. Therefore, a microscopic foundation of thermodynamics is established through statistical mechanics.